Hello, and thank you for attending this presentation on USB 3.0 protocol testing with active insertion testing. My name is Don Schenecker. I am the product manager for the USB protocol analyzer here at Agilent Technologies. In this presentation, we are going to talk about how to speed up the design and verification of your USB designs by doing active insertion testing using the U4612A USB jammer product from Agilent. Active testing can take several different forms. First, it can be simply using a golden device, a device you trust to connect in and monitor and test with. That gives you the first benchmark test of operation. But that doesn't give you any error situations. The next common way to do things is by using some type of generator that allows you to control the commands. However, this has the difficulty of it's usually not normal type operations with. That's where we come in with active insertion testing. Active insertion testing allows us to go directly into a live link and modify packets as they flow back and forth between the two devices, changing command A to command B as it flows through our analysis so you can monitor and test the operations. Some of the key benefits allow you to do common use operation, then where errors occur from time to time, you can inject those errors. Or doing scenario testing, injecting a protocol problem of a specific type. It is also extremely useful for problem replication. When problems are discovered in the field, such as a SCSI command is not quite what you expect, you can insert and modify those commands in real time and verify that the proper procedures are being followed. For doing this, we are using the Agilent U4612A USB jammer that uses quick and easy test scripts to generate error conditions, giving you programmatic control of those conditions. They can be used to inject errors, whether they're physical error, F10B errors, or alignment problems, or injecting CRC errors into the packets themselves, corrupting the ordered sets of the link management protocol, or putting link good and link credit commands out of order, controlling the power interface, the VBus power on USB for self-powered devices. If there's a power outage, how does your device respond? Or completely deleting packets, or testing into the higher levels of SCSI commands, of doing the sense IU and response IU commands and modifying those directly. I will be demonstrating the jammer with the use of the U4611A protocol analyzer. However, it is a standalone unit and does not require the use of an Agilent analyzer for doing these tests. Our first simple test we're doing is I have my device connected to my host, but I have the link flowing through my analyzer and my jammer. So when the host sends a command, it flows first through the jammer to where I can modify that command. And then the analyzer will see that modified command before it gets to the device under test and will measure all the responses. Our first test will be inserting a simple 10B error. So now I will start up my software to do this demonstration, and as I bring up the software, it immediately recognizes I have an analyzer and a jammer on the link. I open it up. These two units are connected together, so they're operating as one unit. I am capturing packets with the analyzer. It has a 9 GB capture buffer. Using all of that buffer, waiting for a trigger condition. In the filter mode, I'm using the default settings, which filters out idle conditions and skip messages, pings, response, and isochronous timestamps. Maximize my buffer a little bit more. Right now, I'm not using the trigger conditions of the analyzer at all. If you want to know more about the trigger conditions, please see the companion video on the U4611A protocol analyzer. But what we are interested in is the jammer capability. The jammer has a programming language that uses the same interface that we use on the analyzer to look for specific commands. What do you want to do in an operation? Looking for data packets or timestamps or mass storage commands? and then operates upon those. For our first simple case, I'm going to say a data packet, drag it over to my state diagram to where I'm going to wait for exactly some number of these events to occur. I can say I want to look for host data packets, 1,000 of those data packets, and when I do that data packet, I'm going to, let's inject a physical layer error, a phi error, a 10-bit error, and we'll inject it to the device. Then we will go ahead and trigger so we know that it occurred. So now when I run my command, I see that data is flowing. There's not much data, so I'm going to add some data by running a batch file that's copying some files back and forth. So this link is active and data is flowing. Going back to my analyzer, I see data flowing, no errors. Let me a 10-bit error into the link. I can see if 10-bit errors, it triggered. I can stop. And what I see is that it immediately takes me into the link where I triggered. Data packet, acknowledgement. The next data packet, header packet start, there was a 10-bit code error in that data packet. Also caused a CRC error, not surprising. My device responded back with a link bad. Host said, let's retry. And it sent the data packet again. So here it was sequence number 7, corrupted, sequence 8, and the communication kept right on flowing along. In our first test, we verified the operation of 10-bit errors. Now we will look at the error conditions that occur with the link management. Testing protocol operations. What if link commands are not equal? Being able to insert things in there, or changing the link management packets, the header sequence numbers. If they are not in order, the link must go into recovery. Or if the link credit commands, if the sequence is not right, the link must go into recovery again. We use these test scenarios. We can implement those with the USB jammer with some very simple test scripts. Now let me show you. I could easily say from the link commands, I'm looking for the link credits from the host to the device, and when I get a link credit B, I'm going to modify, replace that command, and make it a link credit C. I have to make the commands match and let it automatically recalculate the CRC. When it does that, let's add the trigger condition. And let's not do it on the first one again. Let's do it on the 100th of that. Run the little command, run the script, it triggered. I can look at the sequence. Link good occurred. Link credits were flowing back and forth, A, and it went to C. The device immediately went into recovery mode to bring the link back up. So we can see that it's highlighted the CRC sequence error, or the CRCs were good, but the sequence for the link credits was corrupt. For another example, let's look at testing the device classes. Mass storage commands uses a variation of SCSI, referred to as bulk-only transport. That was originally developed in 1999, and it uses sequential operation in a single command. It's now been largely replaced on USB 3.0 with USB attached SCSI protocol, which was released more recently in 2009, and it allows parallel operation of commands. But the basic SCSI commands are the same, so we will do a test using the SCSI command and modify the way those commands are being sent to our device under test. If I go to my jammer, let's simply look for a write command. A write 10. I pull that over. So I'm looking for write 10 commands from the host. And when I get that command, I want to modify that packet. Let's say I want to modify the cache operation. SCSI uses the FUA write directly onto the media, and don't return until that is complete. And so that modifies the time that it takes. Just for variation, let's only do that 1 out of 10 times. And we can let that run and see what the effect is on my commands. So on this link, we'll run this script and capture some data. We see data continues to flow. I will stop, and we look at the data in here, and it continues to flow in its operation. Let me collapse all of these commands down. And we can see the right command, over and over and over again. Let me search for the right 10. Well, if I look at the right command, lock command, FUA is not set. Let's look at the next one. And we can see that this write command has the FUA bit set. The processing time for that 64K block of data took 2 milliseconds, whereas most of the others seem to be taking less than 1 millisecond. In summary, the USB protocol jammer from Agilent Technology allows you to quickly stress the devices under test and increase your confidence of your deployment and the USB protocol operations. It also helps you reduce the development risk, both in the quality and the time it takes to find the errors that may occur. With an intuitive GUI that, when integrated particularly with the Agilent USB analyzer, allows you to do detailed analysis, to do the analysis that you need. Thank you for spending a few minutes with me to look at the Agilent U4611A and B protocol analyzer and the Agilent U4612A jammer, allowing you to locate the intermittent problems on super speed USB in quick and timely fashion. Thank you.